Hello, everyone. Welcome to our, what is this, Wednesday, April 5th, sorry, May 5th stream. We are excited to have you here. It's been a couple of weeks since we've done one of these. We're going back to our normal every other week system that we had before the pandemic lockdown started. So slowly but surely things seem to be returning to normal. We are happy to have you here. I'll let Professor Impey, I'll let you say a quick hello, and then we'll get started with questions. For those of you who are with us, we'll grab questions from the chat. So go ahead and post questions in the chat.
Yeah, welcome everyone. Yeah, we just changed our frequency. The MOOCs were surging during the pandemic, and we were getting an awful lot of people online, even going once every week. But I think once every 2 weeks is a little more manageable for us, and it keeps the questions fresh. So the floor is open for your questions today.
Excellent. The first question is from an email. Wendy Traver asks, is it possible that the speed of light is not a constant and has perhaps increased during inflation and perhaps with the expansion of space-time itself?
That's an interesting question. The constancy of the speed of light is a very important issue in physics, because the constancy of the speed of light is essentially a premise of special relativity. The theory is built around the result, an observational result, the Michelson-Morley experiment that showed that there was no reference frame for the carrying of electromagnetic radiation through the universe, or the ether that the Greeks had hypothesized, a medium through which light travels. There is no medium, it's the vacuum of space. And so to explain that experimental result, Einstein deduced a theory of special relativity which has this constancy and universality of the speed of light as a premise. So then if we like the special relativity theory, which is confirmed thousands and thousands of times a day in labs, physics labs around the world, the question becomes, is it a good assumption? Is it a correct premise? And of course, now with high-speed electronics, we can test the speed of light in terrestrial and lab experiments very accurately, because we can do sub-picosecond measuring of laser light pulses or single photons traveling through experimental equipment, and we can measure the speed of light in a very simple and direct way, distance divided by time. So the speed of light in lab experiments is verified to be constant, independent of the conditions in the lab, independent of where the Earth is in its orbit, and so on. As for whether that's a universal property is harder to tell. We project our laws of physics because there's nothing about them that seems to be specific to the terrestrial situation. And so we assume that light is constant throughout the universe. If light did have a variable speed or variable with time, that would actually have consequences in what we see in the universe with large telescopes. So I think there's weak, not as strong as a lab experiment, evidence that the speed of light has not varied over time in the history of the universe, because when we look out in space, we're looking back in time. But we can't do direct time of flight, point A to point B type experiments on the speed of light anywhere other than the Earth. So unfortunately, that's a rather weak statement.
Excellent. Thank you very much. The next question is, the question is specific, but I think we could talk about it more generally. So Antonio would like to know, says that they're interested in astronomy, but pursuing a degree in computer engineering, but would like to know if they could be eligible to apply for astronomy after getting a bachelor's degree in computer engineering. Can you talk a little bit about what it takes to get into graduate school in astronomy? What are the requirements to get into a graduate program in astronomy, and the kind of backgrounds that you think can get in?
Right. It's an important question because it does come up quite often in these sessions. I'm talking about the American graduate school program, and to some extent, I'm also very familiar with graduate schools in astronomy around Europe. But this is not a global statement I can make. And I'm very familiar with our graduate program. I was a graduate advisor for a decade, and I've been on the admissions committee many times. So in general, and throughout the United States, graduate programs in astronomy or astrophysics take candidates who have a bachelor's degree in physics. That's the most common situation. I would say that's 70 or 80% of the situations. Sometimes their first degree or bachelor degree is in physics and astronomy. Those are not that common, those programs, but that's also obviously appropriate. Sometimes there's a minor in math. Sometimes there's a minor in other subjects to go along with the physics. But I would say the fraction of applicants, successful applicants to graduate programs in astronomy who don't have physics as part of their undergraduate major are very small, under 10%. That's not to say that it can't happen, and it hasn't happened. And computer engineering is one of the fields where a crossover is possible. So I guess my general statement would be it's a bit of an uphill battle against a very competitive program or gene pool to get into an astronomy graduate program without a physics background, because so much of the graduate training when you get to graduate school is in astrophysics. You're taking essentially graduate level physics courses at some point, and then astrophysics specialties. And so the background in physics becomes really important. So you would come in with a pretty big deficiency. Now, it is possible to transition to that program by trying to make up some of those deficiencies in physics by taking online or upper division physics courses ahead of applying for admission, and then it will show in your transcript. Also, historically, the physics GRE, graduate record exam, has been an important part of graduate admissions. Now, very recently, because of understood and perceived biases in the GREs themselves, graduate programs around the country in my field in astronomy have stopped requiring physics GRE, absolutely. And certainly they've stopped keying their entire decisions based on the physics GRE, which some programs used to do. Again, a sign that physics is very important to get into graduate school to do astronomy.
The next question we have is from Hernan Reyes, who is with us live, but also sent an email. And I think there's two interesting questions here. The first one, excuse me, is that do you think it is fair to say that it is generally going to be impossible for us, or possibly any biological organism, to ever explore an exoplanet? And is that a reasonable statement and possibly a reasonable answer to sort of the Fermi paradox?
Let me separate those two questions. The feasibility of humans traveling outside the solar system to another star system. That's obviously far beyond our current capabilities. However, if the question is about whether it's impossible or will ever happen, those are very strong words. And so I'm loath to say it's impossible or that it will never happen. Obviously, humans have never gone further than the moon in 60 years of the space program, and that's not very far at all. Even traveling throughout the solar system is likely to be decades away. And the stars are hundreds of thousands of times further away than the nearest planets. The nearest exoplanets that might be habitable could be in Proxima Centauri system, so they're among the nearest stars. But again, we're talking about 5 to 10 to 15 to 20 light years away, which is hundreds of trillions of kilometers. So the reason I don't say it's impossible or will never happen is that there's one ingredient that would make it possible. Two ingredients, actually. One is more efficient forms of propulsion than chemical rockets. And there's work underway there. And there are simple physics ideas based on fission or fusion, or gathering your fuel in transit from hydrogen, which stops you carrying it along the way. So those are in play. And so those are not showstoppers. There are definitely means of propulsion that are much better than the ones we use now. They just haven't had a lot of research. The second thing, of course, would be just the timescales. Even traveling at a fraction of the speed of light, a few percent, say, it's multi-generational trip. The other ingredient, therefore, is suspended animation, the ability to take the human organism down to a sort of wait state and then reanimate it at the destination. And again, I'm unwilling to say that's impossible, because there's actually signs in medical research that it is possible. There's a lot of progress in medical research just based on resuscitation techniques. These arise out of medicine. They don't arise out of space travel, where human analogs, dogs and pigs, for example, have had their body fluids replaced, and they've been taken into a cryogenic state and reanimated after hours or days, not with perfect success, but with moderate success. So I think given the early phases of that research, it would be very rash to say that that's not going to be possible for us to be taken down into essentially a wait state. And at that point, if we had suitable shielding from cosmic rays and high energy radiation along the way, then it is totally feasible for humans to leave the solar system and reach another star system. It will take a long time, but to the humans involved in suspended animation, they won't really care about that. So what's the time scale? Well, obviously it's more than decades. It's probably a century or more.
Thank you very much. The next sort of follow-up and related question is related to Mars. Elon Musk seems to be, bullish on humans going to Mars and living on Mars, and possibly eventually terraforming Mars. Given the sort of vulnerabilities of humans, even that can seem kind of outrageous or even impossible. Can you talk about what are sort of the reasonable expectations for humans visiting Mars and the current impossibilities?
I think the exploration and eventual habitation of Mars will happen, and the timescales again are decades or more. But I mean, NASA has a staged approach where they'll start with these very clever rovers, then we'll move to bringing back rock sample return. Then those same rovers will start to explore potential sites to locate an initial habitat, and then eventually there will be a habitat where the astronauts are resupplied and don't spend their lives there, but maybe spend a few years there, and then there's a new crew, just like the space station cycles people. And in that staged approach, it would take decades, maybe 40 or 50 years to get to a colony, but you could get there. There are no, again, showstoppers along the way. Yes, there are hazards in getting to Mars and then being on the Martian surface, but they're actually, the radiation hazards kind of pale from the physical hazard of something going terribly wrong and the loss of life from that reason. So whether it's Elon Musk or NASA or some other entity like China is putting a lot of money into its space program, and they're already planning to go to the moon and Mars, maybe not to stay, but to visit, I think it is going to happen. It's fairly inevitable to happen. And part of the reason it will happen is because there are no fundamental obstacles. If you had to bring everything with you, then it would be a huge proposition because it's so expensive to lift things into Earth orbit and get them to Mars. But there's very good technology now that shows how you can use Martian soil to make building material to protect yourself from the radiation, for example. So your building materials are got in situ. You can use the Martian soil and chemically decompose it to create oxygen to breathe, and then hydrogen and oxygen to make rocket fuel. So you can provide, and there's sufficient water frozen or hydrated into the rocks that you can liberate if you choose the right place for your site. So water, oxygen, building materials, and a habitat are all within reach with pretty standard technologies. And that's really the reason I think it'll happen, because there's no fundamentally new technologies that even have to be developed. They just have to be prototyped and then played out in this new environment. I'm not sure Musk will be the first one to get there. He talks a good story, of course. He's been doing extremely well in his program to get astronauts into Earth orbit after a decade of Americans not being able to launch their own astronauts. So it'd be unwise to count him out even on his more ambitious goals. And of course, he is currently in the last year or so doing test flights of what would be his interplanetary transport system. Now, he's had some spectacular failures, and he's always very quick to post the video, so he doesn't try and hide his failures. He is one of these people that progresses in his space program by pushing the envelope. Basically, his philosophy is if you don't break things and blow things up, you're not trying hard enough and you're not pushing the envelope. Now, these don't have people in them at this point, but he is flying people into space. So it's an interesting strategy. It's quite different from NASA's philosophy, which is extremely conservative. So I think in the end, I would actually bet on Musk getting to Mars before NASA.
The next question is from Shiva Manand 1, who's on with us live. The simple question, why is the universe expanding?
Well, the universe is expanding because there was some early event of space-time which injected a lot of energy into the universe. So the expansion of the universe clearly represents kinetic energy, it's energy of motion, but it's a very particular kind of motion because it's an expanding space-time manifold. The word manifold is a mathematical term referring to a geometric construct, and space-time is a geometric construct because in general relativity it can be curved or flat. And so there was obviously some source of energy for the Big Bang and for the expansion that followed. And at this point, we don't know what that original source of energy was. So unfortunately, the question of why is the universe expanding is still unanswered, because that would also mean why did the Big Bang happen? And we know how the Big Bang happened after the very first instant, but we don't know the why yet.
Newtopia is on with us live and would like to know, what kind of moon regime do you think should be created in order to manage the moon's resources? So I'm assuming some sort of a treaty or governmental regime.
Right. So the moon is a resource, and it's not owned by anyone, and nor should it be. And some of these questions are still unanswered. The UN had 2 treaties that dealt with space that were signed by a large number of countries. The Outer Space Treaty of 1965 and the Moon Treaty of 1979. The Moon Treaty essentially says that governments and countries cannot own property on the moon or own the moon or keep people off places on the moon, but it actually said nothing about the private sector. I guess at that time it was viewed as implausible that the companies or corporations would actually get to the moon. So unfortunately, there's not a set of law in place applying internationally that could be supported by international courts to adjudicate conflicts that might arise on the moon, claims of property and claims of mineral resources and so on. So that's a bit of an unfortunate vacuum, especially as we have more countries going to the moon. I mean, America's been to the moon, China has been to the moon with robots, India's been to the moon, Russia's been to the moon. You know, the number of countries is growing, and eventually there'll be people there, and there'll be an industrial activity. And so there's a new regulatory framework that needs to be established. The United Nations is the logical body to do that. But the last time I checked, there are not any active initiatives underway to update the Lunar Treaty, for example, that they did decades ago to the new reality of the fact that we are going to go to the moon.
The next question is from one of our live participants. Rentgen 101 asks, can you talk about what the structures, I assume they mean structures within the universe, like galaxies and large structure, would look like if the background, like the temperature of space, were to increase?
Well, the temperature of space is, of course, now the temperature of the microwave background. So after 13.8 billion years, that radiation from the Big Bang has been stretched by the expansion to microwaves and a temperature of just under 3 Kelvin, 2.726 Kelvin. If that temperature were to increase, there's no reason it would. All the expansion of the universe is going to do is actually decrease that temperature over time, essentially by the expansion factor itself. If it were to increase, it wouldn't actually change the structures in the universe that much because the radiation does not actually do much to these structures. Another way of saying that is that the last time in the history of the universe that the radiation was important relative to the gravity that's formed stars, galaxies, and clusters was 10,000 years after the Big Bang. For the entire subsequent almost 13.8 billion years, gravity has dominated radiation. So even if the radiation somehow became significantly more important or significantly stronger or higher temperature, it would not affect the way gravity causes structures to form in the universe.
The next question is from Pelotilhu. I'm not sure how to pronounce that, but sounds French. Supposing SETI were to receive some sort of signal that seemed convincingly intelligent from another galaxy, the signal would be too old to follow up with. Should we concentrate on searching exoplanets that are much closer to us or mount an effort to reply?
If SETI received a signal, interesting issues would arise. And one is, what do you do with the signal and who do you tell? Now, the people who do SETI have protocols, which they've had in place for decades, actually, of who they would tell. For a start, they do follow transparency, which is appropriate for science at this level. Nobody's going to sit on the signal or hide it or keep it secret. It is almost essentially immediately told both to the International Astronomical Union, to their reporting arm, that's the governing body of astronomers worldwide, and it would be, if they thought it was a legitimate signal, it's of sufficient importance that it would be reported to the United Nations. And the United Nations has an office that doesn't deal exclusively with this kind of thing, but is a liaison to scientific researchers with really important or time-critical discoveries. So there's a mechanism to get it to the world's attention. As for what to do about the signal, well, it would depend on where it came from. Now, if we're doing SETI, we have to target. We can't listen to the whole sky and all objects. So SETI people have targeted their listening, and indeed, the upcoming and current SETI experiments are trying to target fairly nearby star systems, because then at least there's a prospect of having an exchange of signals in a human lifetime, for example. For instance, the nearest stars are 4 or 5 light years away, and there's dozens of stars within 20 light years. So these are targeted systems, but it is true that some of the targets of SETI are much further away across the galaxy, and occasionally SETI does experiments in external galaxies. Well, galaxies are millions of light years away, so any intelligent signal received from an external galaxy would be that old, millions of years old, and really the prospect of a communication is pretty dim, because even if we send a reply, the odds that we're still here in billions of years are pretty low. Most species on Earth only last a few million years before extinction, or they ruin themselves, in our case probably with technology. So these are big issues, and I think it's because SETI spreads its bets that some of the targets, and in fact most of the targets, are fairly nearby in the galaxy, so that if you did get a signal that you believed was artificial and intentional and intelligent, you could reply, and you have the prospect at least of some very slow conversation, but not so slow that it's impossible to carry out.
The next question is from Gurzi Wachu. Are there any scientifically accurate visualizations of what a neutron star might look like up close, or a millisecond pulsar?
Yes, there are scientific visualizations of these things using full hydrodynamic relativistic code in 3 dimensions. So the state of the art of simulating compact objects has progressed pretty far and fast in the last decade or so with the advent of supercomputers, especially parallel code and the speed with which you can simulate these difficult calculations. So a couple of I think on their websites, like NASA has some of these. If you search on NASA and neutron star and simulation, you'll probably find that. Also, these simulations are done by a couple of the national labs. Lawrence Livermore and Los Alamos National Labs do this. So yes, there are actually accurate simulations of what neutron stars would look like. Of course, neutron stars are not visible objects because they're dark. They don't emit electromagnetic radiation. If they have hotspots, they might emit radio waves. So essentially, neutron stars are dark. So you have to use a visualization method to imagine the surface.
The next question is from Astro Admirer. The Earth's, I guess they read a news story that with the quote, "The Earth spun faster than normal last year, according to scientists." Is this statement true, and how can this happen? What are the consequences?
I think I understand what that's based on. So, timekeeping now is at such an incredibly precise level of 1 part in the most accurate clocks are 1 part accurate to 1 part in 10 to the 15. And that means you can measure the year, for example, the time it takes the Earth to go through one orbit, or the day, the time it takes the Earth to spin once on its axis, to tiny fractions of a second accuracy. And in those terms, there are sequential changes in the length of the year and in the length of the day. They tend to be monotonic. They tend to be only in one direction, not not erratic from year to year. The mechanism for the day changing is the tidal interaction between the Earth and the Moon. The Earth and the Moon are tightly coupled because the Moon is a big satellite of the Earth, and as we see, it has one face pointing to us all the time, so which means that the tidal locking is quite tight. And that interaction is gradually transferring angular momentum to the Moon, and the Moon's distance from the Earth is increasing by a centimeter, I think, a year, and the Earth is spinning slightly slower as a consequence to conserve angular momentum and energy. So that's a steady process. I'm not aware of a glitch, actually, that just applies to 1 year. The only thing that could possibly cause that is some high-level seismic rearrangement of the tectonic plates, which would change the moment of inertia or the mass distribution of the Earth, and that would affect its spin rate.
The next question is from one of our live participants. Newtopia again asks, what do you think of SpaceX and Elon Musk winning the NASA contract to land humans on the moon? And do you think that Jeff Bezos's protest is valid?
Right. So SpaceX has had a series of multi-billion-dollar contracts with NASA, initially to resupply the space station. Those were unmanned flights to the space station and Earth orbit, and more recently, as we've seen, to send astronauts to the space station successfully and bring them back. That happened very recently. And then now a third stage is to start to get contracts to go to the moon. Bezos maybe has some right to complain in that his rocket technology, the Blue Shepard and the other rockets that he's been testing, are true rivals to Elon Musk. They're also highly competent technologies. His method as a company, Blue Origins, is to sort of the slow and steady approach as opposed to Musk's go fast and break things. And that has led Musk to progress further and faster along the path that they're both companies are taking. And so I think based on the the evidence in hand, where your track record to do these hard things really matters, that was undoubtedly the reason why Musk was given the contract for the moon mission. What is less clear, however, is the cost basis for the bids. Because when you make a cost basis, are you doing a true cost accounting of the activity, or are you sort of subsidizing it or viewing your activity as a loss leader because eventually you'll get so many contracts that you'll make money? And I think some of the complaints in this arena have been over the cost basis for these contracts as opposed to whether the company could do them or not. But it's very hard to argue with success, and Musk has had demonstrable success in getting supplies and astronauts to the space station.
The next question is from Pelotil Hugh, again, who asks, kind of a follow-up, would we ever dare send humans in suspended animation to far distances many hundreds of years from now without being able to test such a procedure? I mean, I assume the answer would be no, but how long do you think we would have to test something like that before we'd be confident sending them to the stars?
Well, I mean, the answer might be no, but the answer also might be yes, because, people do have, the ability to choose their own destiny. Now, governments tend to not do activities that they know are going to lead to somebody's death. That's not considered a good thing by governments. But being an astronaut or going into space has always been a high-risk activity. Many countries sanction euthanasia, so they give people the legal right, with no consequence, to take their own lives. And if it was viewed that going into suspended animation for generations with an uncertain probability of being reanimated at the other end was just taking a very high risk that you might actually be sort of signing a death sentence for yourself, then governments might let people do that. You would sign a waiver, your family members might have to sign it too, and you would do it. So I don't actually think that fully testing suspended animation for the time scales that would be needed to get to the stars and waiting that long is necessary for it to happen. People, if you look at human explorers over time, from the people who went up the highest mountains to the first people who went to the poles to any number of examples, these people have undertaken extremely risky activities, so risky that the probability of death or not coming back were very high. And I think people will continue to do that. The first people to go to Mars will be facing the same likelihood that it's an extremely hazardous activity. So I think the travel to the stars and the suspended animation will happen without it being fully tested over the time span that's being proposed.
The next questions are two of them that are basically the same question. In zero gravity, which direction does a plant grow? Does it still have a definite up or down direction, or is it up relative to the plane it's growing in? How do plants react?
That's a good question, and there've been, of course, experiments with. There've been a lot of experiments on the space station over decades, really, with seeds, germinating seeds, and seeing what happens. I mean, if you take an existing plant into space and put it in a zero gravity situation, the plant will, of course, be disoriented, and some of its vascular or capillary action will be affected, but mostly it's responding to light and radiation. So I think if you put a plant in zero gravity, an existing plant, and then put it in total darkness or had uniform light all around it, it's not clear what would happen. I think it would be pretty random which direction it shoots into or grew into. Seeds do germinate in zero gravity. They of course have to be in a situation where the nutrients can get to them, because soil will just float out of a tray or a pot. So it's not easy to germinate seeds in zero gravity. They have to be in a contained situation. And I think what I read from a few experiments is that if they're in a truly neutral environment where there's no preference to the light source, and gravity obviously doesn't exist, then it's pretty random which direction they send out their first shoot.
The next question is from Oxbowman, who asks, what are the most promising emerging basic physics insights that might be likely to result in new breakthrough, I guess they say technologies that are useful for optical astronomy, but perhaps you can talk about, just how they might prove insightful in the future.
Well, I think the area of physics that is most likely to play into technology in a way that affects astronomy or astrophysics, but also many other fields of science, is quantum computing. So, the very early prototyping of quantum computers is underway, and these by no means rival any existing computer yet, but as a proof of concept, it's been very successful. So basically, you can create quantum coherent states and then you can turn what used to be in the traditional electronics situation a bit of information, a 1 or a 0, which typically in an atomic level would be a spin up or a spin down, into a combined state that's neither up or down, neither 1 nor 0, and that's called a qubit. And these are coherent way to code information. And in the information theory that attaches to this, you can execute very high speed and efficient forms of parallel processing if you can distribute your information in this quantum coherent way. And so computers based on qubits, as opposed to normal bits in computer science, have been prototyped at the level of dozens or maybe a few hundred qubits. That's not enough to get you very far, but their technologies are being scaled up rapidly, and obviously research around the world now gets hundreds of millions of dollars put into it to make quantum computing a reality, and that will have dramatic effects, not just for science and astronomy and astrophysics, but for everyday life.
We've got a next question from a live participant. Karan Third the Dark asks, string theory predicts the existence of higher dimensions in the universe. Is it even possible, maybe in 100 years or so, to actually manifest enough energy to test string theory practically?
It seems a long shot, because if the basic string theory has compactified dimensions, these hidden dimensions that are on an energy scale that's, I think, 15 or 16 orders of magnitude beyond what we can reach with the highest energy accelerators like the Large Hadron Collider. That's an enormous gulf. And so there's no obvious way that our technologies can directly access those energies. The only two prospects for testing string theory at that level are to somehow get a signature of the reality of string theory and hidden dimensions from the early universe itself. So we do have, ways to look back in the history of the universe and the Big Bang that are already probing tiny fractions of a second after the Big Bang. And if you could get back far enough, you, in principle, could be accessing the realm of string theory and hidden dimensions. And so people are trying to work theoretically into some form of prediction that might be something we could observe perhaps in gravitational waves from the Big Bang. That may be one way the signature might manifest. The other way it might manifest is actually on lab scales, meter scale experiments, which are now underway. So very, very highly precise lab experiments measuring space-time essentially with enormous precision in the lab, in principle have the ability to access not the hidden dimensions directly, but their influence on the dimensions of space and time that we exist in. There's a lot of argument or subtlety about what these influences are, but there are people who are exploring versions of string theory to look for something that manifests on a lab scale, and those experiments are continuing. So there are some prospects, but it's extremely tall order given the energy scales where string theory truly applies.
The next question is from Fady911X. Is Elon Musk really adding value to the economics of space travel? As in, is SpaceX having an effect on market growth and shifting of the supply and demand curves? And I assume also bringing the cost, down for space travel as a whole.
Mm-hmm. Not yet, but it's within sight. So the activities of the private space sector, and primarily SpaceX, but also the other players, have lowered the cost of launching a kilogram into Earth orbit from $10,000 a kilo, maybe a decade ago, to about just over $1,000 a kilo now. That's a factor of 10, and that's really by innovation, and it's really by reusable rockets. The rockets, the Apollo program, and most of NASA's history did not have a lot of reusability of the vehicles or the launch stages, and that's an extremely expensive proposition. So he's lowered the cost curve, and we also know that Blue Origins and Virgin Galactic are planning suborbital flights for a year or two from now, and the cost for those will be $200,000 to $250,000, and there's clearly a market there. So as these companies progress, they are taking their cost curve down to the level where wealthy people, as opposed to billionaires, can afford to do this. And then you're not too far away from people who really want to do it as a once-in-a-lifetime experience, who are just middle-class people being able to do it. So I think that's about a decade away. And at that point, if you look at the numbers of people and the wealth of the countries, of people who can afford that in the middle class, you have a huge market. And so your potential industry is an industry at the level of $100, $200 billion a year revenue. And these are fairly robust economic projections for the private space sector.
Ronash7 would like to know, if someone died on the surface of Mars, would the body decompose in any way? And then I'll add to that, what would happen to the body?
Well, it sort of depends on how they died. I mean, if they were on the surface of Mars and they would be wearing a spacesuit, of course, a pressurized spacesuit, and so there was some mishap and they died. If they were just trapped in their suit, what happened would take place very slowly. If it was just an exposed body on the surface of Mars, then the body would essentially freeze because it's well below zero and very low pressure. So the blood, ironically though, the blood inside would boil before it froze because of the low pressure. So death at that point would be instant. After that though, stasis would set in. I mean, there'd be no decomposition. Again, there's no atmosphere, there's no air, there's no reason for decomposition to happen. All that would happen would be just a gradual attrition of the exterior layers by micrometeorite impacts and cosmic rays and high energy radiation from space. So I think a body on Mars would suffer, a horrible initial fate and bloat out as it froze, but then would pretty much stay intact for probably centuries.
The next question is from Parseval Fusto 1. Does traveling in space for a long time affect human body parts?
Well, our best evidence for this is from the space station, because the other voyages in space we've made to the moon, these were voyages of a few weeks. So that's the furthest we've been from the Earth, but it was a short trip. Whereas in the space station, there are a number of astronauts, several dozen, I think, have had more than a year in orbit, and there are a couple who've had multiple years in orbit. So we have now data on what happens after a year or more in zero gravity, and there are substantial adverse effects. The obvious ones are, of course, loss of bone mass, some level of atrophy of the muscles, of course, because they can't be used in the normal ways. And these are even assuming that you're exercising, because all the astronauts on the space station have a pretty rigorous exercise regimen. But again, it's very hard to operate the body under the normal stresses and counterbalancing forces that it has with gravity. You have to design the equipment very cleverly. So there are those effects. There are some of the more severe effects are actually involve the eyeball, the pressure equalization in the eyeball changes, and there have been serious vision problems among some of the astronauts. So some of these physiological effects of zero gravity have been a little surprising and disconcerting because they're quite significant. Hormone levels change, chemical imbalances can occur in the body, even when you're getting a balanced diet, and astronauts in the space station, again, have a metered out food with very careful regulation on minerals and nutrients, so they do not suffer from malnutrition. So it's still an active research field what all the physiological effects are, but they are actually profound and pervasive. They're not fatal, though. I mean, no astronaut has died from long-term zero gravity, but they have suffered substantial health consequences.
The next question is from Terminator 0907. Is it true that the temperature of the sun is increasing?
Yes, it is true. The sun is burning hotter as it gets older, and that's basically because, and this is very slow. So it is increasing, but it's a very slow and steady process, taking place over tens or hundreds of millions of years, not from year to year. But the reason it's happening is because the sun, of course, is converting hydrogen into helium, and then it has convection, which is mixing the material of the sun. And so as it does that, as it converts from one element or one atomic nucleus, simple proton, to a helium nucleus, it actually reconfigures to maintain its hydrostatic equilibrium, its balance between pressure and gravity. And in that process, it burns a little hotter, and so it changes its equilibrium configuration. And that's going to be a steady process as it ages. And if you project that forward in about 500 million years, well before the sun runs out of fuel, essentially hydrogen, the sun will have got hot enough to put the Earth on the edge of an habitable zone. In other words, taken the Earth almost to the point where the oceans start to boil. So the global warming we're worried about right now was caused by ourselves, our own hand. But the global warming caused by the sun burning hotter as it gets older is a more profound problem, but it's pretty far in the future.
As a follow-up to that question, is it possible that the sun could release a powerful solar flare that could wipe out life on Earth?
That's very unlikely. I mean, the sun, of course, has a solar cycle, a 22-year cycle, and the cycle itself, we know, has impacts on telecommunications and the radiation environment of the Earth. The sun also has super flares, which are, you can see the prominences that have been imaged by NASA satellites, these huge looping whorls of plasma out into space, more than an Earth distance, and release of high energy radiation, and that's damaging to the Earth too. Super flares happen every centuries or millennium timescale, and so they are going to happen. These are not fatal to life on Earth. These would cause a spike in mutation rates. They could be damaging. They would hurt technology, the current technology we have, dramatically, but they're not fatal to life on Earth. So the star is a stable enough main sequence star that its activity, including its super flares, will cause some damage to biology, but not at the level of eradication.
There was recently an announcement of a possible small black hole fairly close to Earth, within, I think it was 1,500 light years. Can you talk about what's so unusual that makes this black hole so small, and are there any implications for it being as close to Earth as it is?
Yeah, small black holes are unusual for an interesting reason, that our best measurements of black holes masses has come from LIGO, where black holes merge, and we get a measure of each of the black holes masses as they merge and then form one black hole. And the LIGO results are interesting because these black holes are pretty hefty. They're heftier than stellar evolution theory would predict. Most of the LIGO black holes are 10, 20, even 30 times the mass of the sun. Now, the minimum mass of a black hole, in theory, is about 3.5 times the mass of the sun. But it's actually very hard to find a black hole that's at the minimum mass or even close to it. And so the low mass black hole that was found recently is fairly close to the minimum black hole mass. And that makes it unusual because most of the black holes are bigger than we'd expect them to be. 1,500 light years is actually not that close for a black hole. Because black holes are the results of very massive stars dying, and massive stars are hundreds or thousands of times more rare than the sun. So we don't expect to find black holes anywhere near the sun, because most stars are like the sun, or actually most stars are red dwarfs that'll die just by fading to embers, or slightly more massive stars that'll die as white dwarfs. So 1,500 light years is fairly close. Among the closest black holes, and it's among the lowest mass black holes, which makes it definitely an interesting object to study further.
All right, we have about 3 minutes remaining. So we'll do one last question from a live participant. David Learning asks, how is the semiconductor shortage affecting the astronomy field today?
It's not been a problem as far as I've seen today, but it will be. And that's because astronomers are fairly active consumers of very high-grade electronics and high-grade semiconductors. That's because we use them in CCDs. All the detectors in astronomy are essentially pure semiconductor. And however, astronomy is not a volume consumer of semiconductors, and most of the astronomy detectors come from a few companies that are highly specialized in making detectors for astronomy. And the last I heard, their supply of the very high-grade semiconductors they need to make these very high-performance detectors is not running out yet. So I think the semiconductor shortage that we're reading about is much more fundamental or profound for big consumers like the car industry than it is for astronomy, which is kind of a niche player. Okay, that was an interesting question to end on, and a good variety as always. So thanks for your questions and for being part of our course, if you are, and we'll be back with you in a couple of weeks. And thanks to Matthew for facilitating, and Vicki for helping also, and Alexander for setting us up today.
Excellent. Thank you very much, Chris. We have not announced the next live session, but it will be in 2 weeks, and we will send out that announcement through our course emails. It will be on YouTube, and you'll hear from us soon. Take care, everyone.